Okay, here we are at part 2. How EIGRP operates. So fasten your seatbelts, hang on. You might need to read this part of the chapter twice. But the first part's fairly easy. It discovers neighbors, much like OSPF does, sends a hello packet, and then exchanges routing information. Says here it is. I'm router 2. Here's what I know. So they exchange routing updates. That goes on, and the hello packets flow every 5 seconds. And they acknowledge and gossip with each other and trade information. And then convergence happens when all of them come together and understand the update information about the network the same way. So that's convergence, an important point. Now, EIGRP works with a composite metric. You don't have to know this in great detail, but it's important that you understand how EIGRP works differently, which can make it a more reliable protocol in some networks. So, got to get back up here. So, it takes a default composite formula is bandwidth plus delay. So if you know bandwidth and delay, those are the two factors that it takes in the most. But it has others. It can add in. You see we have K1, 2, 3, 4, 5. K1 is bandwidth, K2 is delay. K2 is load, K3 is delay, K4 reliability. Alright, so these K values can be added in and weighted to change how it works. But still the basic bandwidth and delay are the key values used in tweaking EIGRP. The others can be configured. Here's what they are. Bandwidth is the interface in kilobits per second. Now when you adjust bandwidth in EIGRP, remember you're just adjusting how the algorithm sees that variable. You're not adjusting the physical bandwidth of the router. But it takes into effect slow interfaces and fast interfaces to get a more reliable routing table. Same with the delay of the interfaces. And then the reliability and the send and receive loads. By default, they are not included in the metric, but you can add them in as you want to tweak EIGRP. So the bandwidth, this is this goes into the weeds a little bit, but you use the show interfaces command to verify your bandwidth. All right, when you do a show interfaces, here it is, bandwidth BW64 kilobits per second. That's what you're using, and then you can configure it that way. To make sure it's right. You don't want to showing faster than it is. But both sides of the link have to have the same value, of course. And here are the interface delay values. If you have fast Ethernet, you have a delay of 100. Ethernet is a delay of 1,000. Gigabit Ethernet 10. So as you can see in 58K, DST1, those are up to 20,000. So these numbers matter in the next formula here, where the EIGRP metric is calculated. First you determine the link with the slowest bandwidth, and then you use that value to calculate the bandwidth, multiplied by 10 million. So you take the delay value for each outgoing interface on the way to the destination, add the delay values and divide by 10. All right. So you take the sum of the whole delay, divide it by 10, and then you add the computed values for bandwidth and delay. Multiply that by 256 to obtain the EIGRP metric. No, you don't need to do this in your head during the test, but this is how it works. The bandwidth plus the delay times the 256, that's the metric you use. And then that's how it weighs them out. And that's this magic number that shows up here in the routing table. That's how you know what this is. This is your metric. And so your metric has to be a certain number it has a value, and it can be compared against other paths that have their own metrics. That's the important point here. So the dual concepts, the diffused update algorithm that runs EIGRP provides loop-free paths with fast convergence and minimum bandwidth usage because of the bounded updates we talked about in the previous section. So, the decision process for all route computation uses the finite state machine, and it tracks all the routes, and it uses the EIGRP metrics to develop the loop-free paths. All right, and it also has backup routes, but it doesn't call them backup routes. Of course, it has to be a little harder than that. They're called successor routes. Successors, actually, the successor is the least cost route to the destination or network. Which means it's the preferred path. All right, it's called the successor, and the feasible distance is the lowest calculated metric to reach the destination network. So the feasible distance will determine who the successor is. So here's the feasible distance. Right, that's the calculated metric we talked about right here. And then the successor is the next hop to know who it is. All right, no problem so far. So just to throw a few more terms into your notebook here, a feasible successor is a neighbor that has a loop-free backup path to the same network as the successor, and it satisfies the feasibility condition. What's the feasibility condition? Well, the feasibility condition is when a neighbor's reported distance to a network is less than the local router's feasible distance to the same destination network. If that's true, if he's got a reported distance less than this router's feasible distance, then it meets the feasibility condition for being a feasible successor. And the reported distance is an EIGRP neighbor's feasible distance. So the feasible distance on your router becomes the reported distance on another router when you tell that router about it. Okay, so with all of that, how does this make sense? So we do a show IP ERG topology, and we see the next hop address of the successor and the feasible distance / successor's reported distance. Now notice the reported distance here is smaller than the feasible distance, so this is the valid route. This route has a successor, a feasible successor, which means the backup route, okay, and the interface. And if that's true here, so, and again, another example, the feasible distance, if the feasible successor was the successor, then it goes on, and the feasible distance. Now, an odd thing can happen. Sometimes there's no feasible successor, because here the reported distance, all right, the 217 here, the feasible distance for R1 is smaller than the reported distance, so there's no feasible successor here. We just have one strong route. There you go, and here's a little flow chart on the dual finite machine. We're not going to go into this too much, but it checks to see lowest, does it have a feasible successor? If it does, it brings it up. All right, this is what happens, when a route changes. Install successor in the routing table and look for a new successor and move on. So there you are. That's the dual feasible successor gets installed, and we have a new successor that goes via on this route. Now that example showing you how EIGRP chooses its routes, its loop-free backup routes. Okay, and there's another no feasible successor example. So with that in mind, go ahead and tackle the second section of the chapter, and I'll be back. Well, the configuration aspects we can do in the labs, so we'll leave that up to the net labs, and I won't be lecturing on that.